because it's really not a bad thing to go through. It's not bad, and it'll go quickly. I gave you the notes so that you have the notes. And mostly they talk about, are samples independent, are samples dependent of each other? Independent samples are two samples that are selected from a population that is not related, from two different things, males versus females. These are independent. City A versus City B, they're independent. What makes them dependent is when they are paired samples or they're the same sample. I take a sample of 50 students and I test their scores now. Then I give them an SAT program and I test their scores at the end of that SAT program. It's the same 50. I test the same group, a before and after, because I want to see was there improvement. That's what statistics is all about. How did this change it? Was this change worth it? So that's why we test our samples. So very, very basic. Here's a couple of good examples. Sample 1. I have the weights of 65 college students before their freshman year begins. Sample 2. I have the weights of the same 65 college students after their freshman year. Dependent or independent? Dependent. It is the same group. So these are dependent. Okay, because it depends what they tested in the beginning, how they changed at the end, right? I have a correlation between them. They're dependent. Versus, I have scores for 38 adult males on a psychological screening test for attention deficit hyperactivity disorder. Sample 2. I have scores for 50 adult females on the same psychological screening test for attention deficit hyperactivity disorder. Independent. They're independent because I took two different groups. Two different groups. And that's all there is to this so far. Independent versus dependent. Okay? Try it yourself. Sample 1. Systolic blood pressure of 30 adult females. Sample 2. Systolic blood pressure of 30 adult males. Independent. They're different. They're taken from different groups, right? Not the same group. Same exact number in each, but they're not the same group. Independent. Midterm exam scores of 14 chemistry students, and sample 2 is the final exam scores of the same 14 chemistry students. Dependent. Because I'm going to look how they did on their midterm, and the same students, I'm going to judge how they did on their final. Okay? This is one of the biggest things used in statistics. We teachers use it all the time. We look at midterm grades. We test your midterm grades and we say, well, we can pretty much figure out what you're going to do on the final based on your same midterm grades. But if I was to look at a different group, I couldn't judge them on yours. I have to do the same group again. Okay. So, when you're testing a claim concerning the difference between two parameters, the mean, the standard deviations, the variances, you're not exactly testing the parameter itself. You're testing the two samples of things. And we begin by assuming that there's no difference in the means of the two populations. That's to say that the population means would be the same. It's like saying they're the same if there's no difference between them. You're going to see these hypothesis statements are slightly different than what you normally use. And we're going to take a random sample from both, and we're going to assume that those samples will have the same sample. Otherwise, we can't compare two things that are not the same. Now, your null hypothesis and your alternate hypothesis are slightly different than what we did. When we tested one sample, when we tested one sample against a population, we said that the mean SAT score for all males is greater than 1200, the mean. We tested the mean against one number. Here's the biggest difference. We're testing the mean of one against the mean of the other. There's no number here. You're testing two samples. So now I'm going to say the mean of the females is greater than the mean of the males. There's no number. It'll be U1 is greater than U2. The means are no different. If they're no different, they must be equal, right? If the means are different, then they are not equal. So here's the major difference when we test two samples. We're testing them against each other. The same rules apply. The HO gets the equal sign. The HA does not, no equal sign. The sketch follows the HA. The rest of this is not going to change. We're going to get a one-tailed test, a two-tailed test, a left-tailed, a right-tailed. All that will stay the same. The biggest change is right here, where we tested against the value because we only had one sample. So we tested that sample against what they told us for the population. And this time we test the two against each other. The biggest difference. And we'll make a little chart which will make life a lot easier when we do this. Our population standard deviations, whenever we do a z-score, are known. We have to know those, otherwise we have a T, and we'll do a T. The samples must be randomly selected, they must be independent, and each sample size must be greater than or equal to 30, or they have to tell us that the population was normally distributed. That doesn't change. Same thing. Here's that beauty of a formula. This piece right here is this. So they're saying this actually is going to be 0, so all you're looking at is this. It's no different, guys, than when we did x minus the mean over the standard deviation. Doesn't that look very familiar? I mean, it's kind of beefed up a little bit, but this is the x, the difference in the x's, this is the mean over the standard deviation. The z-score formula slightly changed a little bit. It's telling you have to take your population standard deviation for each one, divide it by how many are in the sample, add them together, take the square root. That's what goes under here. This is why I don't bother using the formula. It's a little bit confusing, and it's a little bit time consuming, and we have a beautiful calculator step to do for this guy. So, and I thought this was a great thing because a lot of you don't like the calculator. So it kind of forces you to pick up the calculator and to use it. So we're going to use this calculator step to sample z-test. And it makes sense. There's two samples. It's a z-score because we know the population standard deviation. So grab a calculator. We're going to try one. Again, you do the same thing. You make your decisions. Okay. So let's give this a try. A credit card watchdog group claims that there is a difference. Here's their claim. Claims that there is a difference between the credit card debts of households in California and Illinois. So he's going to be the U1. He's going to be the U2. The U2. Yeah. The easiest way to do this is to separate this into two parts. Okay, go like this. California, guys, we can make this section an independent section. I have no problems with that. So our claim says there is a difference. TJ, how do I say in a mathematical statement that there is a difference between the means?
There is a difference. Then you say, wasn't there a problem there then?
Yeah.
Or what?
I know it's exactly what I've been talking about for the past 20 minutes.
I've been listening.
Rebecca, how would you say it?
Well, can you repeat the question?
No.
Oh.
Nick, how would you say there is a difference? Tell them. So if we're different, Are we equal or unequal? U1 is not equal to U2.
I'm sorry, I feel so stupid.
I see, I would.
That's HA, and the HO is the complement. They're equal. So what tail test do we have according to the HA? Two tail test. Now, we're back to z-scores. We're back to z-scores because we know the population standard deviation. So in order to find these guys, we're back to inverse norm. So we're going to take your level of significance and we have to share it for two tails. So we're going to take this and divide it by 2. You can do this right in your inverse norm. 0.05 divided by 2. And you're going to get your cutoff values. Do this something else. 1.96. And positive 1.96. Remember, your curve is symmetric again. We're on a perfectly symmetrical curve, negatives and positives. The only one that doesn't use this is the chi-square, and that's done. Over. Forget about it. So now, we take a look at the sample. Here comes your sample. We surveyed 250 households from each state. So your sample size is 250. Okay. Your mean for the first one and your mean for the second one. Well, they gave us the table. Obviously, I didn't include the table here. So your mean is 4,777, and this mean is 4866. Now, they have to give us your population standard deviation because this is z-score, and the population standard deviation is known. So just write it under here. Keep all of one state here, all of the other state here. So they gave us this for California and this for Illinois. Okay? So we've got everything we need to do. We need to know exactly where these are. Now we're going to use your calculator. So everybody pick up your calculators, not your phones. Pick up your calculators. And I want you to go to Stat, Test, and I want you to come down to number 3. It's a 2-sample z-test. Go to Stats. In this one, they make you put your population standard deviations in of both of them first. 1045 and 1350. God bless you. And then look how nice this is. X1, N1, X2, N2. So go to your table, take your first one, put in the end. They both had 250 in their end. A lot of times the sample sizes are different, and that's okay as long as they're not drastically different. Then put in this one, 250. Now, just like we did before, follow the tail. We have a not equal. Then we're going to calculate. So here's your test statistic. Your z is equal to negative 0.8, and it's z-score, so it's 2. And your p-val, in case you want to test p-val, is 0.410. Was everybody able to put that in on their calculator? Okay, when we do the t, it's even nicer than that.
Where did you get like the extra one in the?
It actually came from the table on the side in your book. I'm sorry, it was on 422. Okay. I said I forgot to copy the table onto my example, so I had to write it. Usually it's either in the words or in the table. Okay. But whenever you see it, put it in the table.
Will they all give us?
Oh, they have to give you that information. Okay, now, all you have left to do is one of two things. If you're testing the z-score, this z-score falls over here somewhere. What is your decision? Fail to reject H0. You could also test your p-val. P-val, level of significance. 0.410 against 0.050, and that's greater. Failed to reject H0. That's it. And then you just go back and you say, okay, if I fail to reject my H0, then could I support my claim? If I fail to reject that they were equal, no. So at this point, can I support the group's claim? No. There's not enough evidence to support the claim that there is a difference in the mean credit debts of the households in California and Illinois. The what? So all there is to this. This is it. Okay? This is all there is to this. Alright, let's try another one. Alright. Read this to yourselves and write me the claim. Read this over and write me the claim. And I might call on you. Sometimes the claims don't come to the end, sometimes they come in the beginning. Where are Keep reading. Sometimes you can read it the last sentence.
He never passed the test.
Wait. The first time.
Okay, Oliver, did you read the claim?
Yes.
What's the claim?
The claim is
Right at the end.
is
there
the
enough
difference.
evidence to conclude there is a difference in the mean
That
annual
means
wages?
Equal.
Is
Not equal to.
is not equal to. Different, not the same. This is the claim. Is this the HO or the HA? HA. HO is that they're equal.
So is it always at the end of the claim?
No. Sometimes they put it in the beginning, sometimes they put it at the end, sometimes they put it in the middle. Whenever you see the word, can you conclude, is there, the claim is, they state that, they say this.
So,
You gotta
I have
look
a
for like
question.
those subtle words.
I have a question.
Yes,
So what is the difference is not equal to?
right.
So
If
when you
it's
know it's
different, if I make $10 an hour and you make something different, do you make $10 an hour? No, so we're not equal. We're not equal. We're
So
different.
when it's gonna say the same, that it's equal?
Then it's equal. Then I make $10 an hour, you make $10 an hour. Okay, let's make a chart. We've got two things going on. We have wages for forensic science technicians for the local and the state. So we'll make local and state governments. So start like this. This happens to be, this is their survey. This is their sample information. They put it first. They're allowed to. So X1 is 55,590. X2 respectively means the first one is local, the second one 950. Thank you. And the second one is 51,100. Now, just because you see that they look different doesn't mean that they will come out different, because you still have sample size to consider and you still have standard deviations to consider. The survey said they had randomly selected sample size of 100 from each one. So N1 is 100, N2 is 100. They go on to give you, assume the population standard deviation for the first one is 6,200, and the population standard deviation for the second one is 5,575. That's where there's a difference here. It says the two samples are independent. At a level of significance of 0.10, is there enough evidence to conclude that there is a difference in the mean annual wages? Notice it also didn't say reject or support. So it's not really giving you a hint, is this an HO or is this an HA? So if there's no different, oh, thank you. If there's no difference, then they're equal. If there's a difference, then they're not equal. So we have a two-tailed test. Same as before. We know this is a z-score because they give us a population standard deviation. You've got to find your critical values. So how do I find my critical values? Mariah. Put it in your inverse norm, and because you have two tails, what do you have to do? Divide by 2. Good. So find me your critical values. Everybody does this.
Negative 1.645.
Good. And positive 1.645. Good. Now, the rest, we use your calculator for. Same as we just did. We come to your calculator, we go to your stat test, we take 2 sample z-tests. We put in your standard deviations are first 6,200 and 5575, and then enter the rest of your information. Once it's in a chart, it kind of plops right in. When we do the T is even nicer because it goes X, X, N, right in a row. This one makes you put your population standard deviation in first. That's how you know this is a z-score. So now put your information in. And both of them have the same sample size. Again, what tail test do we have? 2. And calculate. So you can get a z-score this high. And here's your p-val. Look at how small your p-val is. It's not 6. It's moved this 9 decimals to the left. It's about 0. It's moving it 9. It can never be greater than 1. That's the area under your curve. So it's all the way to the zeros. After you get that, just see where this falls. This falls way out here, and you reject H0. This is my decision. And the rest is the exact same. If you reject H0, that means you have to go along with this one. I don't want this one, I want this one. So since my claim was my HA, there's enough evidence to support the claim that there is a difference in the mean annual wages between the local and the state forensic science technicians. Aaron?
I didn't get that for the Z-score.
You didn't get that for a z-score?
Yeah, for what?
What'd you get?
I got negative 54.
Whoa. Okay, let's take a look at what you put in. Bring up your data. See if you got this in the right way. Maybe something was missing a 0. Check your values, because it shouldn't ever be that high. I would say if you get a z-score greater than 10, less than negative 10, probably not right. Check your values. Did you put in your population standard deviation?
I put in the X score. I got
Okay. That would make a big difference, because they would make so much less than the other one. So they would be so drastically different. Okay? Questions on this? This is how simple this is. But what I want you to get in this is not the